Yeah, okay. This is great to be here. I am entangled on nanofluid topics for many years now, and this conference, which is doing a really good job, is pushing me into the latest state of the art and showing me who is active in this field and which emerging fields are to be seen. So this is great. I have seen a lot of very interesting talks already. I'm looking forward to the rest of the talks, and it's really worthwhile to be here. I thank Mr. Buschmann for introducing me. Luckily, he named the achievements, and he did not name all the mistakes I have made in life already. So let's keep it this way, and I hope I can impress you on these achievements. Another difficulty I have to tackle today is the time of this talk. I know that talking to audience in Spain at noontime is very dangerous, and luckily I'm an old university professor, so I had classes in the early morning, I had classes at noon, and even in the evening, so I know how to handle students just by raising the voice or clapping hands and maybe asking questions, so please be aware, but I will try my best. I mean, the best thing to have is good content and good information to talk about. This will hopefully keep you awake. Okay, so Hanover, nice city, mid-sized city in the northern part of Germany, not too far away from Hamburg. Mr. Buschmann knows it, of course. Mr. Wongweis has spent some years there. Other people may know it, hopefully. It's 500,000 inhabitants, and it has a nice university. At least the main building is looking nice. Unfortunately, not all the other buildings have this appearance, but let's take a look at the main building. This gives good hope. Okay, so I want to motivate my talk. Why am I dealing with radiation? Then I will introduce the tools which we used to look at the optical properties of our nanofluids. Then I want to show at least two applications, or let's say at least one application, the solar thermal power plant. And if time allows, I also want to show the second application we are working on right now at this topic of passive radiative cooling. You see to the right my trials to visualize a nanofluid. We have tried to draw these nanofluids on scale. So this should be nanofluid having 5 volume% of particle load, particles being 10 nanometers in diameter. It looks quite dense. It is quite dense, so it's good to have a picture on these nanofluids. Of course, this is a quite idealistic view. They are perfect spherical particles. They are equally distance between them, so no agglomeration is there, so it's probably not a true picture, but just an idealistic picture. My history on nanofluids is, quite long. You know that there are 3 mechanisms on heat transfer. So there is conduction, where we all started off, I guess. Then we have convection, and also don't forget about the radiation. We started conduction in the year 2001. I was afraid to use the transient hot wire method because I was scared that this electric field, which will build up around the wire when there is an intransient current showing up, that this electric field may take influence on the particles. So I tried very hard to establish a guarded hot parallel plate apparatus. This took us many years to get such an apparatus into good function. We took part in this benchmark study organized by Mr. Bongiorno from MIT. We made a fairly good job, but our uncertainties were not far away from all the other instruments which were used in this benchmark. So I guess my fear on this transient hot wire method may not be true or justified. Our convection measurements were quite involved because I tried to have a constant wall temperature boundary condition. So I used steam to heat up the pipe where the nanofluid was flowing. We made some interesting measurements. I read all the papers from Mr. Wong Weiss, for example, and other, Mr. Xuan. Okay, we saw the enhancement on the laminar side. We had difficulties to see it on the turbulent side. So now I have my home topic, radiation. It's not the last try on nanofluids. This is not the main reason to look into radiation. It's because my favorite topic in thermodynamics is radiation thermodynamics. This is where I have started many, many years back, and I'm always dealing with converting energy from one form to another form. So radiation energy is an interesting form of energy. We have plenty of this energy because of our solar star close by. So it makes sense for a thermodynamic person to look into the thermodynamics of energy, radiation energy conversion. And this is how I start up. So this is a very general type of radiation energy conversion device. You see there's some incoming radiation flux. There must be, of course, some outgoing radiation because you can't skip this one. Then there will be some heat flux going in or out, some power, which we typically want to have from this device. And this would be a very general situation. It could be a photovoltaic module, for example. It could be a solar thermal power plant. So we don't have to be specific at this at this stage of analysis. All we have to know and take into consideration is that the radiation energy is always associated with a radiation entropy flux. So there will be radiation entropy coming in with the incoming radiation. There will be radiation energy associated with the outgoing radiation flux. So we have to use first law of thermodynamics and, of course, second law. So, if we put down both laws and if we solve for the power which we typically want to have from such a device, then we see, as it is clear, that the outgoing energy, radiation energy flux should be as small as possible. Okay, we try. But we also see that the outgoing entropy radiation flux should be as large as possible. So we have to find some surface which allows just for this. Not too much energy going, but a lot of entropy going out with this radiation flux. Of course, always thermodynamic people tell you to keep entropy production as low as possible. You know about that. And we have to learn about the entropy production mechanisms which are associated with handling radiation. Okay, so this is the main driving force. And the emission of this flux is what the engineers can handle. I mean, the incoming flux is given. We don't have too much in ways of influencing this incoming radiation, but it's up to us to design the outgoing radiation. So we have to find something which goes along with this basic thermodynamic considerations. calculating entropy. Okay, please don't be afraid. I will change to nanofluids in a minute. It's just the motivation part. So I hope you understand what drives me into nanofluids. So calculating the entropy of radiation is well known. So these equations, which you see on the slide, have been put up by Max Planck and by Albert Einstein. Max von Laue has worked on this. So these equations are well known, and no, not too much trick on those. You have to know the spectral distribution of the energy of the radiation which you're looking at. You have to know the distribution in the solid angle, so the angular distribution of your radiation. And of course, you have to know the degree of polarization, because it's clear that polarized radiation is more ordered, more tidy, has less entropy than unpolarized radiation. Okay, so these formulas give you access to some examples. So this would be the extreme cases you have in radiation situation. So the spectral distribution has a strong influence on the entropy. The entropy can vary between 0 and the maximum possible entropy would be energy divided by the thermodynamic temperature, which is equal to the entropy associated with the heat flux. So the maximum entropy is associated with the black body spectrum. So if your spectral distribution is like a black body distribution, you have the maximum amount of entropy associated with it. And the minimum possible radiation entropy is associated with laser monochromatic radiation. So this would be almost 0. So tuning radiation properties can give you entropy fluxes between 0 as a minimum and energy divided by temperature as a maximum, black body radiation. So there is quite a bit of tuning possible. Okay, this was looking at the spectral distribution, similar news from the angular distribution. So if it is confined, the radiation confined to one very small solid angle, the entropy will be low. And if you have a distribution on the hemisphere, then the entropy will be high. So these are the methods and the ways of looking into entropy production and entropy distribution of radiation fluxes. I will not talk too much about angular distribution. I will look at the spectral distribution mostly. And I will not talk about entropy too much anymore, but this was the background which has pushed me into nanofluids. Because if you look at such scattering behavior, scattering pattern, which may appear if you deal with nanofluids, then you can understand that a thermodynamic person gets all excited, because such ordered patterns must be associated to some specific entropy. So if I look at these scattering patterns, I think I have a good tool of tuning the entropy which I need to optimize my radiation conversion device. Okay, this is the background of my interest into nanofluids. So the radiation properties of nanofluids are quite flexible. You know that, as Robert Taylor has told in the morning and other people have told, the influence parameters which you have working with nanofluids are quite diverse. So you have particle size, particle shape, particle material, base fluid material, and you have other means of handling the specific optical features of nanofluids. And so this is the connection which I will tell you about in the next slides. It is, well, it will become clear that we have to use Mie scattering theory as a basis. Rayleigh is not good enough approximation, so we better start with the more general me theory, the Lorentz-me theory, which will give you the scattering behavior, and then you can calculate transmission behavior, you can calculate absorption behavior. So if you handle me theory, you have all the information needed for the optical treatment of nanofluids. Please remember that we have all these mechanisms at once, transmission, mostly in nanofluids, scattering, mostly, absorption, hopefully, and we call transflection the sum of transmission and scattering, and extinction to be the sum of scattering and absorption mechanisms, which we see. So also remember that absorption is already a conversion of energy appearance type. So we have radiation energy turned into thermal energy by absorption, but scattering, at least elastic scattering, which I will concentrate on, is just a redirection of radiation energy. Okay, so this is what we will try to tackle. As I said, I went out to Mies theory right at the beginning because the size parameter, wave number, and particle radius A may be in the order of 1. So we are right here at the borderline between Mies scattering and the special region of Rayleigh scattering. So I better take the Mies scattering theory to be able to simplify my problems later and not go with the wrong theory. Okay, so the Mies theory is not easy to tackle. This is why Robert skipped it in the morning, but I will not dwell on this too much right now. You need as an input the complex spectral refractive index, or which is equal to this, the spectral relative dielectric function relative to the absolute value of epsilon. So you need these property data of your material and of the base fluid to get started. And this is one problem. Well-done data of this type is available, but not in the extent which we would need for a big screening event. Okay, and then if you have this input data, then you would calculate the scattering cross-sections, the absorption cross-sections, the extinction cross-sections, and you can calculate these efficiency factors, which is the scattering cross-section, for example, divided by the geometrical cross-section, the area seen by the particle. And these efficiency factors, which we have not only for scattering, but also for absorption and transmission, these are the result of our calculation. So I will not talk about this solid angle distribution, not about this scattering pattern. This will be something we are doing on a separate road. Today, it's only the spectral distribution of these optical coefficients, which we need in our application examples. So this finally is done by a program, and we have the results will be shown in such maps. These screening results I will show in a minute are drawn in such maps where we have the complex dielectric function on the abscissa, and we have the real part of the dielectric function as the ordinate. And so we can choose a material which will give us these values, and we can look up the absorption efficiency in this case, and we can judge if it is a good absorption fluid, which we have right at hand, or if it is not doing a good job. So look at these numbers. Absorption efficiencies can be below 1, which means it's less than the geometrical part, so not much absorption going on. But it can be as high as 30, 40, 50. That means it's a very effective absorption going on. 30, 40 times larger than the geometrical area of the particle. So this results in this map have to be, well, we have to learn how to handle it. So we have to see what happens if you downsize the particle, or if you make it larger, if you multiply the wavelengths by 3, for example, absorption efficiency becomes less. And so you have to develop a feeling of how a material would act on optical properties using these maps. And finally, you come up with, well, we came up with results like this. So we have 3 example materials in this map. For example, the blue line, the dashed blue line, would be titanium oxide for different wavelengths. So the titanium oxide is not doing a good job in absorption. So it's here, it's in this area where we have efficiency factors of less than 1. So this is not the material which we would use to absorb, for example, solar energy. Looking at the red line, this is silver particles. So this is something different. So you see the number 440 nanometers, 390 nanometers, which is very close to the maximum absorption efficiency. So the silver particles, as we have already learned in the morning, are doing a good job if you are out for absorption of the solar spectrum. So, and third example would be titanium nitride. This is going right across the landscape, and it is not the particle material which we need for absorption. So I will stick to silver in my examples. We have to check our calculations. So we did some measurements. First, before doing so, we have to look at our size distribution of the example particles which we had at hand. So we had this particle diameter distribution analysis, and we made calculations for the different particle diameters, and we weighed the results so to get a good picture of the nanofluid with having such a diameter distribution. And then we had the possibility, for example, in this case, it's transmission, which we checked against our calculation. We used a spectrometer for this. We can measure transmission very easily using a spectrometer. So the nanofluid is just simply in a cuvette, and we are looking at the transmitted radiation. And the agreement is okay. So I think this is something close to a validation. You see that we have to change the detector at 800 nanometers, so there's a small discontinuity at this point, but the main features are caught quite well by this calculation procedure, which I have sketched just a minute ago. This is the same for titanium nitride and water as a base fluid. And here you see that titanium nitride is not a good absorber in the visible range. So there's a lot of transmission here. So we will not use titanium nitride to be an absorbing fluid for solar applications, for example. We had some more difficulties in doing the transflection. Remember, transflection would be scattering and transmission. We use an integrating sphere to take this value. So if you have incoming radiation, it is scattered or absorbed. So this will be seen by the detector. But the agreement between the calculation and the experimental result is not as satisfying as we had hoped it to be. Well, you have to remember the simplifying assumptions which we have used in the me theory so far. We have spherical particles. We have to go on to other shapes, but at the moment it's spherical particles. We have elastic scattering, we have independent scattering, and so there are some assumptions until now in our calculation. And we also have some doubt about the quality of our integrating sphere. So this is work in progress to get a better match between measurement and simulation. But I think we are on a good way, as we have seen for the transmission. And this is the way we want to screen a lot of materials to see if these materials, these nanofluids, would be appropriate for a specific job which we have to define. This is another example of our maps. It's not an absorption efficiency, it's an extinction efficiency. So if you have other applications like developing sun creams, sunscreens or something, you would not look at the absorption efficiency, you would look at the extinction efficiency, for example. But the method works for this as well, just as I have shown you before. Okay, so this is our tool which we use in screening different nanofluids to find the optimum, well, what we think optimum application for a specific job to do. The first job, the first example I want to show you is the solar thermal absorption plant. We have had some of this in the morning. And so the door is open. This is a parabolic throw plant which we have in mind. And we want to see if there's a volumetric absorption fluid collecting the solar energy in this pipe in the focus line of the mirror instead of the oil which we use up to now. So remember, this is the conventional plant design. So we have these parabolic mirrors all over the place. Sun energy, solar energy is not very intense. So you have to have large areas to collect some megawatts of solar energy. And this is why you concentrate it, for example, in this way onto this tube, which has some heat transfer medium, which is then collecting thermal energy to put it into a Rankine cycle, for example. So in the morning, we had some information about possibly using heat transfer medium, a nanofluid for this application. So this nanofluid would enhance the heat transfer performance, but it would not be a volumetric absorption fluid. We would rather look into this volumetric absorption, which has already been addressed today by looking at these direct absorption collectors. The idea of doing so is quite old. For example, back in the 1975 by Mr. Miradi, this has been proposed long time ago. But it's a good test for selecting a good nanofluid, because this job is not easy. What do we want to achieve? So look to the left. This is the standard conventional surface absorption device, having a steel pipe, having the oil, for example, the heat transfer medium inside, and the energy conversion path is such that the solar radiation is absorbed at the surface, at the outer surface of the steel pipe. So absorption takes place right here, which makes this place to be the hottest place, not on Earth, but in this device. So the outer part of the surface of this tube will be quite hot. This makes it, this makes a lot of losses possible. So there will be radiation losses, and there will be convective losses, and this is why you have to protect your steel pipe with a glass pipe. The glass pipe will have some vacuum between steel and glass pipe, and this vacuum will reduce your convection losses. And this makes this collector quite complicated. So you have all this tubing and you have vacuum, and this is not easy to cope with all this very lengthy mirrors. So the idea is to use a more simple application. It's a glass pipe with some nanofluid flowing inside, and the nanofluid would directly absorb the solar radiation. So the hottest place would be inside the nanofluid. So absorption takes volumetrically place right in the fluid. So the fluid hopefully gets hot in the center, and towards the wall, towards the pipe, you hopefully have lower temperatures. So convective losses and radiation losses shall be lower than in the conventional case. And maybe you can omit the glass tubing. So possibly, if you do a good job, you can have a very simple absorber device which would ease the market for such plants. Okay, it's a clear and simple idea. As I said, it's already long existing, but it's not easy to realize. I mean, it's quite a difficult job to find the right nanofluid and to make the right volume fraction. This is what we are trying out for. So the first step for developing such a device would be calculation of the optical properties of possible candidates. This is what we have done. I have chosen silver and water as possible candidates for my nanofluid. Then you have to calculate the radiation distribution inside the fluid, which is solving the radiative transfer equation. And then you can put it into a computational fluid dynamic calculation, which finally will give you the temperature profile. And then you have to see if the temperature profile is the way you want it to be, hot in the center and cold to the side. So you don't have too many convective losses. You want to have the laminar flow, not a turbulent flow, because you don't want a high heat transfer coefficient towards the wall. And this is what you have to optimize looking into this CFD simulation. Okay, I will show you some intensity distributions now. Remember the job we have to do. This is the solar spectrum, the red line. The solar intensity belongs to the left of this ordinate. We have then the absorption coefficients of water, which would be the green line, and silver particles, which would be the blue line. And the nanofluid is the black line, which is dominated by the nanofluid, by the silver particles right in the visible spectrum, because water is doing a bad job there, as you know. Water would do a good job in the infrared, but we don't have too much solar energy in the infrared, as you know. So this is why we have to add silver particles or whatever other particles to the water, and this has been highlighted in the morning in some talks. This has to be discussed quite carefully. I don't want to go through all these wavelengths which I have prepared, but look at the results. This is the full spectrum right at the beginning. The job you have to do is to find, for example, the right volume fraction. If you have too many particles inside, then you have too much heating close to the wall. You have backscattering and too much absorption right in the wall region, which would make the fluid hot here, and you would have high losses to the tube wall, which is not the aim of this project. So you would rather have the maximum temperature, the maximum intensity at the center of the pipe. So you have to fine-tune your volume fraction, and you see these numbers. The volume fractions are very, very low, as we have learned already in the morning. So you don't need much particles in your water, and the effect on the optical properties is quite intense. But you have to be careful about the proper volume fraction. So if it's too much, which would be, for example, the green line, then there is no radiation intensity in the center of the pipe. So this abscissa is the radius from the center towards the wall. So there's nothing left over. All the radiation is caught right at the tube wall. And only at very small volume fractions you have the maximum of the radiation intensity in the center of the pipe where you want to have it. Okay, now I could go into the individual spectral parts, but it's not new information. This 400 nanometers is part of the spectrum where we have the particles working. So water has low influence, particles have the high influence. And so this is why very low volume fractions would do enough to do this good intensity distribution. And okay, we will skip 700. We can look at the infrared region, which has this distribution, as I said already, that there's water dominant. The particles have almost no influence anymore. So this is the infrared region where you could skip the particles if it's only the infrared, which would be the thing for you to look at. Okay, so we had to do some validation on these measurements as well. We had to validate our optical properties, and we had to validate this radiation intensity. We made an experimental setup, a simple channel with a nanofluid flowing. We looked at the temperature profile evolving, and we have luckily got a good match between the temperature profile along the z-axis, which we calculated, and the temperature profile which we have seen by the infrared camera. So this method works, and next step would be to build a modified cycle. We would use not the standard cycle. If we have this nanofluid working, we would have a direct apparatus, direct cycle, and we would use a flash evaporator to get the steam for the steam turbine. And this flash would also keep our nanoparticles away from the turbine. So as we have checked, the nanoparticles will not evaporate, so there will be almost no nanoparticles in the vapor phase. So this is why such a flash evaporator would be, I think, a good idea on this modified cycle. We checked on this evaporation because I am not sure if nanoparticles evaporate or not. I think if they're very, very small, they may be in the vapor phase, but in our case, we checked and we have done some vigorous boiling in such simple apparatus, and we have seen not one nanoparticle in our vapor phase. So there's no fear that we will have a turbine problem using this kind of setup. Okay, the radiative passive cooling is a very interesting idea where we need optimum nanofluids, or nanosolids better to say, and where our screening is needed. We are doing this right at the moment. So please let me take 1 minute to look at this type of passive cooling. It has been in literature around for some years now, so it's not invented by us, but by other people. We are making, we want to make use of the atmospheric window. So you know that spectrum in the atmosphere has a gap where there is almost no absorption, only high transmission. It's between 8 and 13 micrometers. It's called atmospheric window, and if you emit this region, then you communicate with space, 3 Kelvin, and you can cool even if the sun is out, and this would be passive cooling if your outgoing radiation is higher than the incoming radiation. This would allow for some cooling effect on your device. So you need a very specific nanoparticle to do this job. This is shown here. It has to be a transmission of close to 1. in the atmospheric window region, and it should have almost no transmission on the other part of the spectrum. So this is an example of selecting the proper nanofluid. You have to look at the entropy, which I told you at the beginning. So the entropy household has to be taken care of. So you're not completely free in looking at these nanofluids. But this is a very interesting field of application, and I hope that I can tell you about this maybe in the second international conference on nanofluids. Yeah, so what did I do? I told you that, I told you something you know, that nanofluids have very interesting optical properties. I have shown you how to calculate these properties. I guess most of you have known anyway. I made one example on the volumetric absorption of the solar thermal power plant. I just touched radiative cooling. But the main message connected to the beginning of my talk is that radiation heat transfer, not only connected to nanofluids, but all over the place, needs more attention. And radiation energy conversion is very much at the focus at the moment, because we have to do something with our energy conversion theories. And especially Spain, I think, has enough possibility to use, to make more use of solar energy as it is right now. It is good already, but could be improved, I guess. And this is true for other countries as well. And this ends my talk. I want to thank you for your attention, and thank Mr. Lange and Mr. Fuchs and Mr. Eggers for helping in preparation of this talk. Thank you.